most people were here for the first talk, but not everyone, or
Little.
yeah. No, I mean, I want to know if I can just like continue, or if I need to sort of recap.
No, I think you should assume you should continue. Yeah.
Okay.
Okay. So now we have Mike's field seminar talk on computing with Calabi-Yau threefolds.
Okay, so yeah, so the idea here is that we have X is a Calabi-Yau threefold. We might be interested in other dimensions, is K3 surfaces, four-dimensional things, but we'll just stick to this one for the moment. And in fact, we will be giving it, we will suppose that X is equal to the zero set of some polynomial F sitting inside of this P of sigma, where sigma is equal to a simplicial fan arising from so we take delta is and delta seric. I do have to give a little notation here. So these are a reflexive pair of polytopes, of lattice polytopes. This one's inside of M, this one's inside of N. Okay. And then we take a triangulation of this polytope. We use that all those, it's all a star triangulation, so everything contains the origin, and we use that to get this the sigma that which is a fan, and that gives us the toric variety, and that gives us the Calabi-Yau. So our goal, I don't know if we have a single goal. The overall goal is to compute stuff that essentially, to compute stuff the physicists asked me to compute is really what it comes down to. But also I have my own interesting ideas. So we want to compute things about X. One thing, by the way, I forgot to mention, or I didn't have time to mention before, is that, you know, these are a reflexive pair and it's a duality, right? What happens if we take X and then we make a new thing by flipping these around and do the same process? That was actually really what Bottorff was interested in, and he proved that they're mirror symmetric to each other, and we'll say something about what that might mean in a bit. But so the physicists are very interested in this in part because of the mirror symmetry. Mathematicians are interested in. I like what Dave Morrison said to me 20 years ago. He said it's like being handed down to you the stuff that physicists were doing that people didn't understand even at that time, and still probably mostly not. And he said it's like being handed down mathematics 200 years in the future, and it works great, but you don't really quite know where it came from or anything like that. But in any case, so the physicists want to know various things about X, and because the geometry of it in sort of determines a lot of the physics and things. So they're always going about, they have always new things to try finding in this game. So the question is, what do we want to compute? Okay, well, we're going to talk about some, but let me at least sort of say a couple things. So one thing we might like to do is the Picard group of X. Okay, so the Picard group is you take all divisors, mod linear equivalents, and you just take the free abelian group generated by all those things. It's not free abelian anymore after you mod out by the linear equivalents. But at any rate, so you have that. And for most varieties X, there's no chance in doing this. Even for an elliptic curve, which is a Calabi-Yau one-fold, there's no chance. Well, in that case, it is the Picard group is essentially the elliptic curve. It's infinitely generated. You know, it's not anything great. And even yeah, so this is going to be a situation where the Calabi-Yau threefold is in the sweet spot. It clears some of the difficulties in the low dimensional stuff and isn't as bad as higher dimensions. Okay, the Hodge numbers. These are all things that we'll talk about just a little bit. This is these are important pieces of information about a variety. Whenever you have a variety, you want to get it. This is hard to compute. The Hodge numbers, on the other hand, at least in principle, you can compute using sheaf cohomology, which in principle you can use Macaulay 2 for, but it's actually quite an onerous computation lots of times. So anyway, we would like to be able to do that. Intersection numbers. If I intersect two subvarieties, like two divisors, or actually, if X is a threefold, if I intersect three divisors, I expect a finite number of points. How many points do I get? Essentially, is what I want. Actually, if I'm given a D as a divisor in the Picard group, what can I say about it? I might want to know, okay, is that a very ample divisor, or is it an ample divisor, or is it NAF, or is it even effective? I mean, how do I even know any of this information? So what can we say about D? Some of this information is we know how to do, and some other information is extremely difficult to get. Okay. Then there's also birational geometry. I don't know how much we'll get to this one. This is sort of more sort of current things I'm interested in right at the moment. But for instance, if we have here we'll have the Neff cone of X, the effective cone of X. These are all a bunch of divisors, and you take all the ones that are there, and then somehow we're going to make cones out of them, and then we want to understand what these things are. These might be infinite, so can we actually compute them anyway? So that's sort of what we're doing. Okay. So this is these are the geometric things I'm interested in. Other things you might be interested in. Yes, before I say that.
Increasing the dimension uniformly makes things harder.
Oh, it sure does, doesn't it?
Intuition for why.
I'm going to explain that in just a bit, okay? As to what this is. Yeah. Yeah. So there are cases where some of these things are not finitely generated. That's right. So does that mean we can't compute it? That's an interesting question. In the cases we're doing though, that one will not be general enough that we're doing so that so we will have a better chance. That's not special. That's too special in moduli. Yeah.
Yeah. Are these things that physicists want to know, or the mathematicians?
So in general, the physicists would like to know all of this stuff. They also have. I haven't even mentioned cohomology of divisors and things like that, which we know how to do and everything. They want to know. They want to be able to find divisors with certain properties. They would also like to understand all the chambers of the effective cone as it moves around and things like that. So there's, what they would like to know. And we got whole papers on it by just computing some things like this, and then they've taken that example and gone through and gotten interested in relations between weak gravity conjectures and things like this, and so some of these things were I don't know, they're mostly the thing. At this point we know how to do most of those and so on. So they're interested in trying to find other things. The birational geometry is fairly current. There is a recent paper of Batrev though, where he runs the minimal model program for hypersurfaces and toric varieties, which is something I'm interested in talking with anyone who's interested in that. This is on the edge. The minimal model program with Calabi-Yau it's sort of the case where it doesn't quite handle it. Or at least it didn't used to. What else do I want to say about this? Yeah, okay. So anyway, that's some of the things we want to compute. But I was starting to say there are some other things, and this is something I've done with Hal Shank, and then he talked to McMaster on this at one point. So how about it just in projective space? Suppose these are all hypersurfaces in a toric. But what if you don't care about that? What if you just want the ideal of a Calabi-Yau in projective space? All of these things are projective if they get into projective space somewhere. So how can we see what the resolutions are or the structure of the ideals? I'm very interested in that too. Except, again, I'll explain a couple complications along the way. Okay, so here are some Picard group kind of basics. Okay, so we're going to use the following. So X is going to be a Calabi-Yau threefold. And that means that we have the properties from this morning that we know about. And I'm going to take the short exact sequence on Z maps into functions on X, maps into non-zero functions on X. This is the exponential sequence, right? This takes a function f and maps it to e to the pi f or pi I f or something like that. And then the integers are in the kernel of this. So anyway, so we can take the long exact sequence of this. What do we get? Well, I'm going to start with h zeros. I don't care about h1. I'm going to start here. h1 of O of x, h1 of O of x star, to h2 of x comma z, to h2 of O of x. And it goes, keeps going in both directions. What are all these things? Okay, this is a long exact sequence. We know by the definition of Calabi-Yau, which is totally awesome, we get that these are zero. And always h1 of OX star is the Picard group of X. That's a set of line bundles, the group of them. So what does that tell us? That tells us that this thing is isomorphic to h2 of xc, which is a finitely generated abelian group. So this is very different from the case of curves or even surfaces. And we know we can say exactly what the rank of the Picard group is. It's the rank of whatever this is. It's topological and things. For K3 surfaces, we can't even do that. So we've cleared out, because we're just a little further up, we've cleared out and made these things nice. What is this thing? This is going to be equal to some number of copies of Z. We're going to use H for that number, plus some torsion subgroup. Okay. For this talk, we're going to assume that there's no torsion. The Picard group X is equal to Z to the H. Okay. So a couple things about it. You might say, well, come on, that's pretty restrictive. Remember that there are 500 million deltas in the database at reflexive polytopes of dimension 4. 16 of those 500 million have torsion. Really a small number. Okay, so we're just going to ignore it. One can handle it, although I would say that at the moment, getting all the algorithms to handle the case with torsion is still of interest. And it's not just because of the Macaulay 2 torsion in the Cox ring that has caused the problems in the past. It's that we don't know how to compute certain things in that case completely. I'll explain more of that also later. What's cool about this, though, is that it's just like this is essentially the same as for toric varieties. Divisors are given by a list of integers, and it's discrete information all the way. It's infinite information. If I want to know, for instance, which ones are effective, one way to do it is I could scan through every single one of them, run some computation, do it, but that's infinite. So I don't know how to exactly do that. But we could take, for that one, we can actually take a finite part of it and figure out which of these things have that property. But anyway, this is the Picard group, and that's one of the things we would like to do. We will do that in just a bit, but instead, I want to also, before we get there, talk about Hodge numbers. Okay, so I don't know if I'm just, I hope that this level is okay, but if you want me to speed up, let me know. But in any case, I think it's still worthwhile to talk about this. So HPQ by def of X, but for any variety actually, is the dimension over the complex numbers. I guess this is over the complexes of HQ of omega P of X. Okay, so this is a Hodge number, and where the ranges P and Q are numbers between 0 and the dimension of X. It's 0 outside of that range. And these have all sorts of symmetry, these numbers do. There's a Poincare symmetry, there's Serre duality, Poincare duality, Serre duality, and things like that. So in general, if dimension of X is 3, there's the Hodge diamond. which we might write as H00, H10, H01, H20, and so on, H11, H02, and so on, H30, H2. I'm only going to write one more line, H03, and then it keeps going this way because it's blocked in with 3 on each side. In Macaulay 2, if you ask for a Hodge diamond somehow or another, you just get a matrix. So it's not a diamond anymore, but this is what it is. So for X at Calabi-Yau threefold now, what does this look like? Well, a lot of these are pretty easy. Most of them follow by symmetry. So H00 is one-dimensional. So lowercase h, yeah, is the dimension, right? So this one is 1. These are just the cohomology of of O of X, which we have there. So H1 and H2 are 0, and H3 is also one-dimensional because of duality, since it's the same as this number. Well, these, and then there's a symmetry back and forth, actually from Hodge theory or whatever. So those are 0, 0, and then that's 1. So that's what you have here. There's one number here. We'll call it H11, because that's what it is. And then here is H21, but that's the same thing as this number here, which we'll also call H21. And then it keeps going. So here we have 0, H11, 0, no, it's just 0, 0, and then 1. So this is the Hodge diamond of a Calabi-Yau. There's 2 distinct numbers that one wants to know. There's H11, which, by the way, is the H, which is the rank of the Picard group. Okay, so you can see that from this information. H21, so this is in sub. So anyway, we have 2 different numbers. Mirror symmetry is fine. There's a lot to what it means, but find an X prime such that the Hodge that H11 of X is equal to H21 of X prime, and H21 of X is equal to H11 of X prime. It is a totally weird thing to do. These numbers, once you get to know what they're about, this is just very, very strange duality of some sort. And it's and this is where what happens is that for these hypersurfaces of this toric variety, Botrev essentially proves that these Hodge numbers here are flipped between the 2, the delta and the delta circ. So in that sense, this is it satisfies this version of mirror symmetry. Mirror symmetry is a big, large thing. It's really the equivalent of 2 conformal field theories, and then what this is one incantation of what happens in one part of math for what that means. Okay. Okay, so the first thing is, how do we compute these 2 things? So it turns out that there's this one is combinatorial information, and this comes from Danilov and Kovansky from work in the 80s, and actually probably even in the 70s, but version I know is from the 80s, and then Botrev in his paper in 93. Okay, and how does it work? What they do is they use the Hodge-Deligne theory. So Deligne has this whole thing with mixed Hodge structures, and it turns out that if you're looking at hypersurfaces of a torus or these things, you can actually compute what that's all about. And this is a great algorithm. This is one that I had a undergrad work on, which is actually pretty intensive for an undergrad to work on. And I still would like to get it really bomb-proof in Macaulay too. And this works for hypersurfaces in a toric. and of any dimension and things like that, as long as it's sort of what's called non-degenerate. So we need a little bit of language here first in order to state how this works. I'm just going to state the result of that because we just don't have time to go through it, although it's very cool stuff. So here I have my two polytopes, and over here I also have my fan sigma. Okay, and now if I have a face here of this thing, I'll say let's call it theta circ. Okay, so theta circ is going to just be some face of this, and there's a duality here we were talking about in the first hour, that this goes to some face theta of opposite dimension. So vertices here correspond to facets here and vice versa, but also works in lower dimension. So here in this case, since we're dimension 3, if this is dimension I face, this is a dimension 3 minus I face. So a facet is dimension 3, goes to a vertex here. So and vice versa. Okay, so those are all the case. And then we're going to define for any face on either side, L of theta or theta circ, it doesn't really matter. This is the number of elements, and theta intersect the z to the lattice. In this case, it's 4, but in general, it's whatever the size of m is. And L star of theta, the notation is this is the number of interior points, interior lattice points of theta. Now, when I say interior, I mean relative interior, right? If you have a polytope which is not full dimensional, you just want it in its dimension thing. Okay. So for instance, if this is my face in some higher dimensional thing, and that's theta, L of theta is 9, L star of theta is 1. Okay, so that's all it is there. And now here is the formula. This is, let's see, I want to have a little room for this theorem. And really, this is an exercise that's in this paper using the Danilov-Khovansky algorithm. Okay. At first, I used to mean that I thought that this was like, oh, not so bad of a paper. It's just an exercise. But in reality, the main thing that I think he's really doing here is also showing that the singularities are under control. So anyway, so here is this theorem. H, remember, is our name for H11. I just am calling it H1H so I don't have to keep writing Z of H11 all the time. This number of X, so this is a X could equal V of F contained in P of sigma as above. This is very special to the situation that we have this pair of polytopes and we're doing it. If we are finding some other thing, then this formula doesn't work. By the way, this formula doesn't depend on the triangulation here. So it's just this. So here's the formula. It's L0 of delta circ minus 5 minus the sum over all faces of delta circ theta naught of codimension 1 of L star of theta. I have a mistake on what I wrote. This theta is not, its dual face is this theta. Okay, so if you look at, no, actually it was right. It's the number of interior points of theta. No, I'm what? Oh, I see what you're saying. Yeah, this is the number of lattice points in here, minus 5. We'll talk about it in a second. And then this is getting rid of some, and then there's another term, and this term is where we have this is summed over all faces theta and theta 0. Okay, but where theta 0 has dimension 2. So it's a two-dimensional face of delta circ, and theta is a dimension 1 face of delta. So it's an edge of delta. So, okay, so this is the way it works. Dimension 2 here goes to dimension 1 here, and I'm summing over all lattice points, theta is 0, theta circ, and theta is just the dual face. Okay. Well, I'm summing over all faces actually, and what I'm multiplying by is I'm taking L star of theta circ. So that's the number of interior points of this triangle or this two-dimensional. This will be not necessarily a triangle. It's the whole face, and times the L star of theta. Now remember, theta is an edge, so it has 2 points on the edge, and there's a bunch of points on the inside, and this is the number of points on the inside of it. And when I first saw this formula, okay, first of all, when I first saw the formula, there's like typos in here, and I mean, there's like there were at least 3 typos in this formula when I first saw it, and I had no idea if these were supposed to be related to each other, or it was just very hard to parse. But then it turns out this is a not trivial. This is an easy formula to understand, and we can sort of see why. So we're looking for different divisors on X. We have a whole lot of divisors. Every ray of sigma gives us a divisor. Well, how many does it give us? Well, the origin is 1, so I can get rid of that. So it's really the number of rays minus 4 somehow. This is really the induced number for the toric variety. Okay, that's how many. If you take all of those things and you had a ray that you had a sigma that used all of those things, this would be precisely the number. The minus 5 is really then, because of the delta 0, is minus 4, and the way you do the way you do equivalence of divisors is that there are these 4 linear relations coming from the rays, actually dimension of delta number of equations. So this formula actually makes sense in higher dimension. You would have to put a minus n or minus n minus 1. Anyway, that's that. But these guys here, these are like these are interior points in a facet. I already told you that we leave those out, and the reason is because if I have one of those, it's like blowing up a point. And if you blow up a point, when you take a hypersurface, it was going to miss it, because you can have it miss any point you want. So these things become 0 on the toric on X. So these become 0 on X. They just don't intersect it. And so, in fact, this whole number here is really the amount induced from the one we have. This one is a little more interesting. So the way I think about it is, suppose I have theta naught is a 2-dimensional face. Let's say that this is my 2-dimensional face, but I happen to have an interior point. Okay, so this is theta naught over here, and it has these 4 points are going to correspond to divisors. And then what does theta look like? Theta over here looks like an edge. There's 2 points somewhere, and then maybe there's some points in the middle, maybe not. Okay, and then what happens is that if we consider this divisor in the middle here, it turns out that, so if this is given by xi equals 0 in the Cox ring, okay, then what is this? This is happening, remember, on the other side, where we get to actually take our polynomial. This is where f equals 0. Is one of our equations. That's the sum of all the things in delta. So delta is 4-dimensional, but suppose it's like this, and then this is theta here, but delta is this huge 4-dimensional thing, and f is the sum over all the monomials in that. But if you also set xi to be 0, remember what xi was doing? It was taking the distance from the ith face. So what basically is anything off of this thing goes to 0. So then f equals xi equals 0 implies that we get a single polynomial from this. But the way that this works is that this is going over the algebraic closure. This is going to factor. And so we're going to get a whole bunch of new divisors coming out. I mean, it's just, you can just see them come out. So you get a whole bunch, for every one of these, that's every one of these, you get this number of new divisors. You actually get that plus one. There's three here, but you get 4 copies of it. But you already had one divisor, which was the sum of all those things. So I don't necessarily want to get into this much, but this whole term here is actually a very cool term. None of these divisors that you get from this are actually toric anymore. So they're a little harder to deal with. There is a definition that physicists use. X is called favorable. If this term is 0. The thing is that you don't really need to do that. But it turns out that there are a lot of non-favorable polytopes in the database, but there's also a huge number of favorable ones. And so if you just are interested in trying out things, don't mind doing this. But if you actually want to really see how it works. Luckily in Macaulay 2, this has been worked out, and so that when you actually ask for the intersection ring, it will give you all of these divisors as well. Okay. Yep.
Related to favorable, non-favorable, and behave with respect to any of the other questions that.
So the annoying thing is that if that's 0, then that's essentially the same as saying that the Picard group of X and the Picard group of the P of sigma, because we got rid of all those ones, are the same. So we can move things back and forth. And it's just technically just a lot easier to deal with. But you know, the other ones, this divisor that breaks up, it turns out it breaks up into a bunch of disjoint things. And each one of those is just a P2. So so it's actually, in some ways, it makes it simpler, but technically it's a little more annoying. So it doesn't make it simpler though. Cohomology computations become much harder in that case. So
In that case, meaning when
so if it's favorable, cohomology computations are much simpler because all of your divisor classes are coming from the toric variety, so you can use all the toric stuff. As soon as you have a class that's not coming from the toric, then you have to put in the ideal of it somehow, in which case that can cause complications. I think it would probably be okay here, but I haven't actually really tried it that much. Okay, so this is a good time to sort of mention what the database kind of looks like. So this is the Kreutzer-Skarka database. In the late 90s or somewhere in the 90s, these guys were making code to write down all reflexive polytopes, first in dimension 3 and then dimension 4. And it's really very cool. And it was a programming sort of achievement to be able to handle that many polytopes, because they actually had to handle many more polytopes in order to prove that was correct. So I forget how many H11. I think there's only like one or maybe a couple, but and H11 is equal to 2. So they're organized by what the resulting H11 value is. Okay, and H11 equals 2. There are 36 polytopes. And each one of these, and all favorable. Okay, and the Picard group of each one of these things is then Z2, with 2 exceptions. 2 have torsion, like a Z mod 3 torsion or something like that. It's very minimalist amount of torsion. For H11 equals 3, there's 244 polytopes. All but 1 favorable. And the one that's not favorable is just as easy to handle for a lot of problems as the others. But nonetheless, you have to still deal with it. And here, except for 2 examples, also mostly, well, this is always the way it is. Picard group is just the H11 number. So it's just triples of numbers. Just dealing with these is pretty good. H11 equals 4. I think number goes up to in the thousands or something like that. H11 equals 5. It's about 16 or 20,000, and there's a lot more non-favorables there, but not a huge number yet. But as it gets larger, I think somewhere in the middle. I mean, H11 equals 10. There's millions of these polytopes, and the largest one, by the way, is H11 equals 491, and there's one polytope. By the way, if I switch the numbers delta and delta circ here, and the circ and the and theta and theta circ, that's the formula for H21. So and that's because of the mirror symmetry. But at the time they weren't sure of it, so they proved that as well. So
what do you mean by the highest one?
So of all the examples in this database, there's 500 million of them. The largest H11 value, that value up there that appears, is this one.
Oh, I see.
And this was favorable too.
Is it expected that for H1 higher, there are no favorable?
No, this one's favorable. They all have favorable, but they also sometimes don't.
Yeah, but for a higher
Like
H11, there is something that they say it is expected or not?
Yeah, so actually what is known is that as you go up, I think it's around 100 or so, anything higher than that has to be elliptically fibered or something. There's some geometric thing that is true. What's weird is this the largest known Calabi-Yau? It is the largest known one. That's an easy question. But is this the largest known H11 of a Calabi-Yau threefold? Well, the way I just stated is yes. But is it the largest one? And the answer is, who knows? But Mark Gross was telling me about, he has a conjecture that is related to this, which is known to be true for elliptically fibered ones, but it's only a conjecture in this case. And it's some reasonable sounding thing, that something has to be less than or equal to 12 or something. You take that thing, you move it around, you put it into here, and this is the bound you get. It's very, very, very amazing, actually. So it's expected that this is the largest one. If it isn't, then this conjecture is false. Although I don't know if there's any real good evidence for the conjecture, except for this maybe. And so the question is can someone find higher ones? That's a good question. These are already huge. If you try to look for Calabi-Yaus in projective space, you know what H11s you're going to find? 1, 2, maybe 3. We've actually seen some with 3 or 4 in these products of projective spaces because it's the number of products that you have for the most part. And but you never see any of the other ones. They just are embedded into such huge spaces. I mean, this one is embedded into a staggeringly huge space. So anyway, I don't know how to deal with that. But I guess the point is that that favorable is actually a reasonably large enough number that you can deal with it, but it's nice to not have to deal with it. Okay, so anyway, so this is the Hodge numbers. Actually, that kills both the Hodge numbers and the Picard group directly. There are other ways of computing these things. One can use cohomology to help you do these things because H11 is a cohomology group and so on. And so we have some alternate checks to make sure that everything is correct as well, but they don't work in the larger cases. Okay. Okay. Geez, did I start at 135? No. Shoot. Okay. So the next one is the intersection ring. Okay. I think for the moment, because of time, I'm just going to deal with we can deal with it whether it's favorable or not. But if it's favorable, so if I take A, which is the cohomology ring of P sigma, comma Z, what is this? Actually, I don't know about Z. Oh yeah, that's an interesting problem. Over Q, I know what it is. So here's the trouble. P sigma is only simplicial. So there are 3 types of toric varieties. There's non-simplicial, simplicial, and smooth. And that in my book. And the non-simplicial ones are bad. The simplicial ones are good, and the smooth ones are great. Okay, so those are the general range. The reason that the non-simplicial is bad is that they don't have intersection rings. So we can't even do this unless we take a simplicial thing. However, if it's not smooth, it's only defined over the intersection numbers are all over Q. Okay, so we can do that, and it's pretty easy what this is. This is going to be Q adjoin T1 up to Tn, and where n is equal to the number of rays of sigma. Okay, and so we have that, and then we have modulo and ideal I. What is I? I is given by the Stanley-Reisner or Reisner or whatever ideal plus linear equations from the rays, from in this case the four linear equations from the rays. Are you all familiar with this kind of thing for the intersection ring of this? This is the sort of thing you would see in any book on 12 varieties, and but it works fine if it's simplicial. But now suppose we want to get the intersection ring of X. How do we do it? Well, this is pretty easy. So in Macaulay 2, there's a package called Schubert 2, which does intersection theory and things like this. And the first version of the intersection ring stuff was done using that. It only does induced in intersection rings, so it would not know how to handle the non-favorable case. But nonetheless, here's the way it works. So let's now consider X in P of sigma. How do we do intersection in here? So we have, let's suppose that we have D1 to Dn are our toric divisors. Okay, so these are the ones corresponding to the rays over there of the thing. And then we'll let D sub I equal, by definition, Di hat intersect X. So this is a surface on X. X is a threefold, so these are surfaces. So what I can do is I want to calculate intersections here. So I want to calculate, say, Di dot Dj dot dk. So for any indices I, j, and k in here, what do I get? Well, this number is equal to, when we lift it up to this variety. So it's the di hat dot dj hat dot dk hat, which are elements that are actually, when I say that, these are really the T sub what, T sub I, T sub j, and T sub k over here. Dot X. Okay. But now the class of X is equal in that ring to the sum of the D sub i's. So D1 plus dot dot D1 hat plus D, this is the on V, Dn hat, which is equal to T1 plus dot 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 plus Tn in this ring. Okay. So how do I calculate this? I just take, so this number here is really going to be Ti, Tj, Tk times the sum of all these things. Okay, that's what it is. Except that actually you have to, this is going to give you a monomial, and you have to have the integral. So this thing here is take the coefficient in an appropriate manner. Take the coefficient of the element in of a number of points. That might be a little too vague, but basically this is what you have to compute. But what is this? So I want the ideal. I want the whole intersection ring. How do I get it? So so the proposition is that H star of X comma Z is the following. It's equal to, basically, I want to know when this product is zero. Actually, I want to know when any product is zero. And the way I can tell that is as if when I take that and multiply it by this, it's annihilated. So what that is, to be annihilated means that it has to go into something that when I multiply it by the sum of the t's, I land up inside of I. So that's an ideal quotient. So this is going to be, in the favorable case, this is going to be z adjoin T1 to Tn modulo I. All of those equations are over z. So I'm going to write that as Iz and colon T1 plus dot 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 plus Tn. So this is the intersection rate. And it's actually easy enough to handle the non favorable case as well. You have to just know something about how they interact, but I don't think I have time for that. Okay. So anyway, this is pretty good. Here's a few things, by the way. If I take di times dj times dk, what kind of object do I mean, this is a triple intersection. What is it? Well, if ijk is equal to a face of sigma, remember it's a cone in there, and on a two-face of delta circ. Okay? If it's on a two-face of it, this number is equal to L star, let's call it two-face theta circ, and then it's the number of sections of theta, the dual face, the interior points plus 1. Okay? And that you can calculate by just looking at the polynomials. There's not like anything really hard going on there. And what is it if it's not that? If it's three things, okay, I'm supposing that I, j, and k are distinct here. If they're not, then we have to do some more work. Okay, but otherwise it's just zero else. So if basically your triangulation is just telling you the geometry on your variety, it gives you exactly which ones intersect, but it also gives you this is directly on X itself without going through the toric variety. And it's a smooth variety and it works over Z. Okay, that is not where I want to stop. The other question that I wanted to say, but I'm not going to have much time for, is one thing I didn't mention before. Suppose I have two Calabi-Yaus. I want to know whether they're topologically the same thing. And there's an old theorem of this guy CTC Wall from the 60s that actually solves this problem. And maybe I will state that because we implement this and use it. So basically, so X and X prime, if they're two CY3s, not necessarily of this form, you get two polynomials from each one. You get the intersection form. Oh yeah, I should have said what the intersection form is. This, if I take x1, t1, x's are just new variables, xn, t, and yeah, I'm not doing this right. I want it into the number h here. I'm just going to state it briefly. So x and x prime are homeomorphic or homotopic to each other or diffeomorphic to each other. As far as I can tell, for these, they're all the same, but I have no idea exactly how to prove that. So are homeomorphic / diffeomorphic. If and only if h11 of x is equal to h11 of x prime, h21 of x is equal to h21 of x prime. These are topological numbers. And then also we have the cubic intersection form. So if I take x1, it's what I was trying to write over there. I'm just going to say f of x of t1 actually, what I'm tripping over here is I'm using the number of variables of the that are arrays, not the number of H11 variables there are. And what I want is the one in H11 variables. So I'm going to say x1 to xh. This is the cubic intersection form. Is equal. There exists a change of coordinates. In GL of H comma Z, where this thing change of coordinates phi such that that's equal to phi of f of x prime. So you have an invertible change of coordinates that changes one. And then there's another linear form, xh. This is the C2 form. The second Chern class is equal to phi of the second Chern class of this one. If these four pieces of information are the same, then they are topologically the same thing. And what's kind of cool is we can go through all of these things. So for instance, of these 36, each one, by the way, has one triangulation of to account up to equivalence. Okay, so so each one really only has one such thing, and there are 29 different topologies. It's pretty easy at H11 equals 2 because this is a 2 by 2 matrix, no problem. 3 by 3, no problem. 4 by 4, problem, but you can start to do it. 5 by 5, but really harder problem, and higher than that, I don't know how to do it. Okay, but we were able to go up to at least sort of that far. But I also have the code, which we're not doing right now, and I can show you how to use it, or I can show you at some time if anyone is interested in that. I would very much like help working on this package as well. It does all of this stuff. It also does some of the birational geometry and various other things. So, so I think I will leave it there. Thanks.